So for the second order, m equal to 2, g2n is equal to k2 f1n plus g1n minus 1. Now we can put that value of f1n from here and g1n minus 1 from here after delaying it. f1n is equal to f0n plus k1 g0n minus 1, where f0n is equal to xn and g0n minus 1 equal to xn minus 1 we have put here, and g1n minus 1 is g1n minus 1 k1 f0n minus 1 g0n minus 2. f0n minus 1 is equal to xn minus 1 and g0n minus 2 equal to xn minus 2, because f0n equal to g0n equal to xn. We know it by the initial conditions, and after multiplying k2 and taking the yn xn minus 1 common, we have this value k1 1 plus k2, xn is multiplied with k2, and this is the coefficient, is coefficient 1. So we can check it out again. g2n has the coefficient in reverse order because it is 1, it is alpha to 1, it is alpha to 2. So again the coefficient are arranged in reverse order. Filter coefficient 1, alpha to 1, alpha to 2. Okay, this is also alpha. Are in reverse order again. So by assuming this test, by checking it, that we can find out that g1n and g2 f1n are just the reverse order polynomial. That is, g1n is reverse order of f1n. Coefficient of these are in reverse order. So we can simply put it gmn by generalizing this equation for m equal to 2 and m equal to 1 by studying these two equations. gmn will become k equal to 0 to m, alpha m, m minus k, xn minus k. We can again check it here by putting 2. Alpha 2, suppose we are putting 2, alpha 2, 2 minus 0, alpha 2, 2, okay, and xn 0, xn minus 0. And second value is alpha 2, 1, that is k equal to 1, k equal to 1, will put, and m equal to 2. Then it is alpha to 1, xn minus 1, and third value is when we put k equal to 2, k equal to 2 minus 2, that is 0, alpha to 0, alpha to 0 is always 1, remember it, and the value is xn minus 2. So again, so this is we can see that it is, these are the reverse. Suppose we will put alpha m, m minus k is equal to beta mk, some other form of coefficients beta mk, and where beta m is equal to alpha m 0 equal to 1. Maximum value of coefficient this one is minimum value of coefficient this one equal to 1, which have we assumed initially. This value we have assumed initially. Now equation will become gmn is equal to k varies from 0 to m, beta mk xn minus k, and this is very important equation for g polynomial. Okay, and it is the beta coefficient, and it is also seen, it can be seen that beta mk and gmn are in coefficient for this function, g function. Betas are coefficient of g function. It is same as that alphas are coefficient of f function. It is the same. Okay, please remember it, this equation, because we will need it later. Now in linear prediction, these lattice filters are used in prediction filters, in prediction error filters. In linear prediction, xn minus 1, xn minus m plus 1 is used to linearly predict the signal value xn minus m by use of linear filter. Application of this linear filter is in linear prediction with coefficient minus beta mk. Okay. When we use the data in x reverse order, xn minus 1, xn minus m plus 1, it means suppose x5, x4, x3, x2 and so on, reverse order, then prediction is known as backward prediction. Prediction is shown by this cap. This cap shows that it is a predicted value. X cap n minus m is equal to minus summation k varies from 0 to m minus 1, beta mk x n minus k, where betas are the coefficient of filter, and this filter is signifies by g. Okay, this filter signifies by g. So g filter, gn function is used to signify this filter in reverse order because it is polynomial of because it is its coefficients are in reverse order of that of Fn. So this type of prediction filter is known as backward prediction filter. Backward prediction filter, because in this case data is run from reverse order. It is because its coefficient are in reverse order of that of Fn. So Fn is, conclusion is what? Why Gn is needed? Gn is needed to form a backward prediction filter. Conclusion: for forward prediction we use Fn, Fmn, and this is the forward prediction. X cap is for prediction, x cap n is equal to minus k varies from 1 to m, alpha m k, x n minus k, x is the inputs and alphas are the coefficient of filter. Okay, and in Z transform form it is fmz is equal to amz xz. Xz is input, am is that polynomial, or it is also equal to hmz, that is that transfer function, and it is equal to output of that filter, prediction filter in this case. And in it is in z domain, now it is in time domain. Fmn is equal to alpha m, that is convolution sum. We have already studied it, it is just for the conclusion. Convolution sum of input and alphas coefficient, where initial value of alpha m equal to 0. And for backward prediction we will predict the last value x n minus m minus k equal to 0 to m minus 1 beta mk x n minus k. And similarly backward prediction, just for similar to the forward prediction, there is a value for gmz equal to bmz xz, where xz is again the input, bmz is the corresponding to this polynomial, reverse polynomial basically. bmz is the reverse polynomial of amz, and gmz is the output of that backward prediction filter. Now again in time domain, gmn is equal to k varies from 0 to m beta mk xn minus k, and it is also convolution sum. You can see it is a convolution sum between coefficients and inputs. Okay, and relation between forward coefficient and backward coefficient is obviously they are in reverse order. So beta mk is equal to alpha m minus k. It is in reverse order. Reverse order means suppose k equal to 0 to 1 to m varies from k is varies from 0 to m. Suppose k is 1 and for m is equal to third order filter 3. M is equal to 3. Suppose k equal to 1, then beta m1 is equal to alpha m 3 minus 1 2. Beta m1 is equal to alpha m 2. Beta m0 is equal to alpha m 3. Just reverse order. And again because alpha m0 is equal to 1, so beta m is equal to 1. And similar to that of alpha, beta m and coefficient and bmz polynomial are basically z transform pair. That is, it is in time domain, it is in z domain. As that of alphas, we have studied in alphas that amz and alpha m k are z transform pair. It is in time domain, it is in z domain. It is z domain, it is time domain. Okay. Now for the relation between these two polynomials, because these are reverse polynomials, bmz and amz. So we know that bmz then z similar to that of amz. Bmz is z transform of beta mk, which we have studied later, last slide. K equal to infinite minus infinite to infinite beta m k z raised to power minus k. It is a z transform pair because beta mk and bmz are z transform pair. It is in time domain, it is in z domain. So putting this value, because we know that minus infinite to minus 1 coefficient are there is no coefficient or non-zero, zero coefficients, and m plus 1 to infinite there are again no coefficient or zero coefficient. So coefficient lies between 0 to m. Coefficient have non-zero value for k equal to 0 to m. Okay, because it was mentioned already. Coefficient value lies between k equal to 0 to m. It is also very important. Okay, these are the conclusions. And now Again, we have just put the value of coefficient from last slide. Beta mk is equal to alpha m minus k, and we have put here, and doing some mathematics, put m minus k equal to L, so L k equal to m minus L, so limits will be changed accordingly. K, when k is 0, L is equal to m, when k is 0, when k is 0, L is equal to m, and when k is equal to m, L is equal to 0. You can check out from here. Okay, these limits. So limits k varies from 0 to m means L varies from 0 to m. Again, it is in this direction, it is in this direction. So L varies from 0 to m, and just putting the value of m minus k is equal to L, alpha m L, z raised to power minus k, k is now m minus L, k is now m minus L minus m plus L. Now m can be taken out because it is not in summation. Z raised to power minus m is taken out, and z raised to power L remains. Z raised to power L can be written as z raised to power minus 1 raised to power minus L for just convenience. Okay, then this form, you can see that this is structure of, from equation number 4, amz is equal to, we know that amz also alpha mk and amz are z transform pair. It is in time domain, it is in z domain. Amz equal to k equal to 0 to m alpha mk z is to minus k. Suppose we put z is replaced by z inverse, then equation will become z is replaced by z inverse, z is to okay. Now this equation and this equation is similar, so we can place amz inverse here. This equation and this equation is similar, amz inverse here. So now by this equation, equation number 12, we got the relation between two polynomials, that is polynomial amz and bmz, and these are reverse polynomial. Bmz and amz are reciprocal or reverse polynomial, that is coefficient are in reverse order. Now further, we know that lattice structure is fmn is equal to fm minus 1 n plus km gm minus 1 n minus 1, and for the mth order we have that value from this lattice structure slides, which I have again and again I have put here. Suppose lattice structure slide, and it is mth form I have placed here, recalling multiple times. Now we can have that z transform of this equation because it is n discrete time domain. We have put this, it's in z transform. Fmn corresponds to fmz, fm minus 1n corresponds to fm minus 1z, km is constant, gm minus 1, n minus 1, n minus 1 delay, this delay is shown by z inverse, and it is gm minus 1 z. Again gmn, gmz, km constant, fm minus 1n, fm minus 1z, and gm minus 1 n minus 1, this delay n minus 1 delay corresponds to z inverse, and again gm minus 1 z. And initial conditions, f naught n is equal to g naught n equal to xn. Initial condition is also taking out in z domain, f naught z equal to g naught z equal to xz. Now simple procedure is that just divide all these equations by xz on both sides of equality. Divide by xz, divide by xz, divide by xz. Second equation, divide by xz, divide by xz, divide by xz. You can check it out. Or last equation also divide by xz. So this is the form. Now reminding the equation number 7 and 11, which we have studied in last slide also, that is gmz equal to bmz xz and fmz equal to amz xz. These are the conditions, these are the relations between polynomial input and output, polynomial input and output, polynomial input and output. And we are calling this relation here again, and check it out that fmz upon xz is amz, fmz upon xz is amz, gmz upon xz is bmz. Just putting the values, amz equal to am minus 1 z plus km z minus 1 bm minus 1 z, and again in this equation bmz km am minus 1 z plus z inverse bm minus 1 z inverse. These are standard equations for polynomials, and these are in forward direction. in forward direction. So equation number 13 is known as forward iteration for forward polynomial, and equation number 14 is known as forward iteration for reverse polynomial, because here a and z is used, which is forward polynomial. It is reverse polynomial b and z. So it is forward equation for forward polynomial, it is forward equation for reverse polynomial. And we can put these equation in matrix form also. You can check it, amz bmz, and this is in matrix form 1 km km1 am minus 1 z z inverse b m minus 1 z. Multiplying this form, multiplying this and this form will relate again the same equation in matrix form. Now conversion of lattice coefficient to direct form filter coefficient. Okay, for this we will recall the equation number 13 and 14. Equation number 13. This is equation number 13 and this is equation number 14. Recalling this equation number 13. Okay. And also recalling equation number 4. Equation number 4 was simple amz equation. Equation number 4 was amz equal to 1 plus k varies from 1 to m alpha m k z raised to power minus k. This is equation number 4. Okay. So putting this equation for amz, equation putting for am minus 1, limits minus m minus 1, and for bm minus 1. For bm minus 1 we know the equation. For bm minus 1z we know the equation. As we know, beta m and alpha m are related with this equation. Okay, beta m and alpha m related to bmz is this equation. bmz equal to this one, and beta mk is equal to alpha m minus k. So using these two equations, we have just solved this equation, and simply equating coefficient of equal power of z inverse, solving this equation, and equating all the powers of z inverse, and recalling an initial condition, we generally obtain the relation between coefficients of forward coefficient alphas, alpha m equal to 0 equal to 1, alpha m equal to km. We need not to go for expression for this one because it is very not required. And alpha mk equal to alpha m minus 1 k, alpha alpha m minus 1. This is the result. You can check the result. If alpha, it is already iterated last time, because it is said that k1 is equal to alpha 1 1, k2 is equal to alpha 2 2, and so on. So it is previously detected, but it is a new result which says that for any value k for mth order, we can have this equation, and by this equation we can find out the value. Now again, to solve this forward equation in backward direction, two forward equations in backward direction, we just put the equation number 14. Check this equation. This value z inverse b m minus 1 z can be taken from here. This is the same value. So this value is equal to bmz minus km am minus 1 z, and this value can be put here. So simply putting equation number 14 into equation number 13. Putting equation number 14 into equation number 13, and that bm z inverse bm minus 1 z is replaced here. That is equation number 14, and amz is multiplying further, and solving this equation. amz equal to 1 minus km square am minus 1 z plus km beta m z. Okay, and then finding the am minus 1 z is equal to amz minus km bm z upon 1 minus km square. This is step down recursion, because this is step down recursion used in Schur cone stability test. We will use it later when we are discussing Schur cone stability test, and it is step down or reverse recursion. Why? Because in forward recursion, when we put the value of m equal to 3, suppose when we are calculating a3z, we need the values of past value a3 3 minus 1 2 a2z, and b 2, 3 minus 1, b to z. It means a to z and b to z corresponds to new value, forward value, present value. But in this, we need to have present value and we will find out the past value. Suppose a3z and b3z we know, and then we will find the a to z. It is in reverse direction. In this case, we are calculating a to z with respect to, with the help of a3z, and in this case we are calculating a3z with respect to a to z. That is, we are moving in forward direction in this equation and we are moving in backward direction in this equation. We are checking out the past values in this equation, we are checking out the future values in this equation. That is what is forward iteration, and it is reverse or step down recursion. Okay, the same, it is in z domain, so we can simply apply the put it all in the time domain, and we can find out that, because we know that AMZ and beta M are Z transform pair. So it is in Z domain, then it is in time domain, alpha M minus 1k. We are already know that A and alpha are Z transform pair. It is in time domain, it is in Z domain. Alpha AMZ is alpha MK, KM is KM, and we know that KM is equal to, from last equation, KM equal to alpha MM. Multiple times we have told it, Km equal to alpha mm, and BMZ is equal to beta mk, because beta m, yeah, this is known written as alpha mk and AMZ are Z transform pair, beta mk and BMZ are Z transform pair. So it is Z domain, it is time domain. We are just converting the Z domain from time domain, and Km square, Km is represented in alpha mm point ohm. So this is the coefficient in time domain, and this is the polynomial in Z domain, where A and B are, A is the forward polynomial, B is the reverse polynomial. Okay, now we will do some examples of these.